Hi guys, in this video I'll make you understand the structure of Niagara like a real pro. If you don't know what I'm talking about, Niagara is an Unreal Engine tool for creating particle systems. It's very important to have it in our arsenal, since it opens so many possibilities for what we can visually achieve, including real-time fluid simulations. Moreover, if you're already fluent in coding shaders, it won't take you long before taking confidence with it. And that's because particle systems are essentially shaders too. That's right, even though I have to specify that now I'm referring to the ones that run the simulation stage on the GPU. If you remember my very first video on this channel, I did a little presentation of what a shader is. There, I listed 4 types of shaders: vertex, pixel, compute and geometry. Then, I went on explaining in further detail the first 2. Well, this time we're dealing with a compute shader. While the vertex and pixel shaders have a well-defined purpose, which is to process triangles and pixels, the compute shader is a general-purpose one. By that, I mean that the data a compute shader can take in and spit out can be totally arbitrary. With Niagara, we are using it to compute the transformation matrices, that is position, rotation and scale, of the particles that compose our effects, along with their velocity, acceleration, aspect and much more stuff. So, let's stop the digression and let's start to dissect this very cool tool to understand its structure. As you can see, this Niagara system is now containing 2 modules. The blue one represents the system, the orange one the emitter. What does that mean? Niagara is composed of several parts, which are organized in a tree-like structure. At the very base, we have the system, which is identified, again, by this blue module. We could say that it represents the actor itself, so we can have only one of that inside each graph. Subsequently, the system can contain one or more emitters, which, in turn, contain all the particles that compose our effect. Of course, we can have multiple emitters. Each one will contain its own particles, which can be completely different from the other ones. It follows that, by respecting this hierarchy, all the data available to the system is visible to emitters and particles too. The data available for each emitter is also available for their respective particles, but not for the system, and the particles' data are not available for anything else. By knowing all that, we can also understand the order of execution of all these modules. System first, emitter second, particle third. This compartmentalization is shown once more by the panel that lists all the variables currently allocated in the Niagara system. Niagara makes very intuitive to understand to which module every data belongs to with the namespace system. These are essentially prefixes added to the variable name depending on where it was created. One thing we can immediately see though is that the 3 namespaces we talked about until now are not the only ones this panel is showing us. We have some more of them, with more or less self-explanatory names, which we are about to discuss one by one. The engine-provided variables are read-only values that come directly from the engine itself. They give us infos about the renderer, like the delta time, or about the actor that owns the particle system in the scene, like its position in the world. The user variables are read-only values too, but they can be created freely inside the system. They are the direct communication line between Niagara and the game logic, meaning they can be written and read by the blueprint or code. On the same note, we find the Niagara Parameter Collection variables, which have the exact same role of the Material Parameter Collection ones, if you already know them. These variables can be only read from the system, but they aren't actually in the system. They are saved in an independent asset in the content browser, which means they can be written from multiple systems at the same time. The transient variables are essentially local variables, which can be written or written freely everywhere in the particle system, but lose their value each time the simulation moves from one stage to another or from one module to another. They can be used as a temporary storage of a value that is going to be used shortly after, but doesn't need to be remembered. The module output variables are transient values too. The only distinction is that they can contain potentially useful data that's automatically exposed by some of the modules we can use to build our effects. Lastly, the stack context variables are persistent variables that you can access freely from everywhere in the particle system. One important thing to notice is that Niagara helps us a bit understand what can be accessed from where by automatically hiding and showing the available data within our selection. Let's now go back to the graph to study better the elements inside the modules, to understand in which order things are done. As you can see, each of the elements composing the particle system are further subdivided. All of them have in common the spawn and update sections, while the particles are missing the settings one, but have the event handler section. Moreover, in the emitter module, we can find a fourth element ignored until now, the render, which I'm going to illustrate better in a minute. The common sections I was mentioning earlier, spawn and update, are the equivalent of the blueprint events begin play and tick. In fact, the code contained in the spawn section is executed only once when the particle system is spawned or loaded in the level for the particle system and the emitters, while for the particles is executed at their birth. The update sections are instead executed once per frame, as long as the particle system is on. In the settings sections, it is possible to modify some properties that define the system or emitter. There are some differences between the two versions of these sections. The most important ones, in my opinion, are that in the system one you can manage the user parameters, and in the emitter you can choose to run the simulation on CPU or GPU. The event handler section in the particles can be used only if the relative emitter is running the simulation on the CPU. By using that, it is possible to make different emitters communicate, so that one emitter particles are sending data to another emitter when a certain condition is met. Lastly, the render section handles the visual appearance of the particles after the simulation for each frame is done. To do that, it grabs a bunch of useful data from each particle, which can be found under the bindings voice. Now it's time to talk about how code is actually written in Niagara. There are several ways of doing that, which I would rank in relation to how pro you want to go about that. Nonetheless, the modules that you can stack in each stage are the building blocks. Let me explain better what I mean. Such modules can be freely added in each programmable section, and they have to be stacked in the order you want them to be executed, from top to bottom. The ones that come with the Niagara package are basically puzzle pieces that you can combine to achieve your goal. It's very important to notice how each exposed parameter in each module can be linked to a variable to read the value from, or can be calculated by stacking other operation submodules to achieve a more complex result without any virtual limit. This is essentially the very basic way you code in Niagara, and trust me, you can go pretty far with it. One downside though is that the more complex the expression I want to build, the more unreadable everything becomes, due to the extreme indentation. In that regard, you can notice how nice Niagara is, trying to translate everything to HLSL for you when you close the drop-down menu. And that's the alternative way you can take to try to make a messy stack like this more tidy and readable. You can replace everything with a single module that lets you write a single line of HLSL code into it. Notice that the code you write here must be composed of a single line and it doesn't want the semicolon at the end. If you want to read variables in that line, be sure to write the namespace of it, in the form of namespace.variablename. If this is still not enough, you can create your own modules completely from scratch with the Scratchpad. Inside here, you can work in a node-based environment that resembles the material editor quite a lot. One very important thing to notice is that every built-in Niagara module is actually built like this. In fact, we can access its code by double-clicking on it, a very useful thing to understand what's going on under the hood and learning new stuff. Lastly, for the real programmers out there which feel physical pain when they have to deal with nodes, Niagara offers a special node. You can add to the graph a custom HLSL node, which is done way better than the one in the material editor, where you can write actual code with any number of inputs and outputs. While we are here in the node graph, it is worth noticing that in this sub-environment we have available two more namespaces for our variables. The input one are the ones that expose to the user the editable values. The local variables are essentially transient variables that are not visible at all outside the graph. The last thing worth mentioning are the namespace modifiers. As you surely have already noticed, some of the variables have two namespaces. This second one, the modifier, can be added to the variables to further specify their origin. For example, the owner one does it with the engine variables that contain data relative to the actor owning the particle system in the scene. It's also possible to create new modifiers of this type freely, to label more clearly each variable. Moreover, some special namespaces modifiers add special properties to the variable itself. For example, initial is used to read the value that same variable had in the spawn stage instead of the current update one. It goes with it that you have to write down the namespace modifier too when writing HLSL code in Niagara. This has been more of a boring lecture video than anything else, but I honestly think that you can't pull out the very best out of Niagara if you don't have a good understanding of this structure, where things are placed and how they communicate. Let me know if you're interested in some VFX topics and they will be discussed in future videos.